In this tutorial, we are going to talk about two other nuclear reactions besides decay reactions called fission and fusion. So first we'll cover fission, what is fission, and then second we'll talk about what fusion is. A fission reaction is a reaction where you take a large nucleus and you split it into smaller pieces. So if you look at this picture that I have here, we have something called a particle accelerator, and a particle accelerator does exactly what it says. It accelerates something like a neutron, and it shoots that neutron at our target nucleus, the nucleus we want to split. And when it hits that nucleus, it splits it into a whole bunch of pieces. So some of those pieces are just going to be single neutrons, and some of them are going to actually be new elements. And in the process, it releases a massive amount of energy because it's splitting or it's breaking the strong nuclear force. So when you break that strong nuclear force, it releases massive amounts of energy. So this picture is a picture of the fission of uranium-235. And so our particle accelerator shoots a neutron at our uranium-235. And of course, as that splits the uranium into a bunch of parts, it releases a bunch of energy. And then of course, if you have more uranium-235 in the sample, then those resulting pieces will fly off into those uranium-235s and split them, and then of course those resulting pieces would fly off if you had more uranium-235 out here into them and split them, and then you end up causing what's called a chain reaction. And every time you split the nucleus of one of these uranium-235s, you're releasing a whole bunch of energy that can be used for a number of things. So probably the nicest use of fission is that you can power small towns with these splitting of these nuclei and releasing of all that energy. And so this is a nuclear reactor, or at least a diagram of a nuclear reactor. And so you've got your core where you have loaded your sample of your fissionable isotope, so maybe uranium-235, into that core. And then you've got, of course, a little particle accelerator somewhere in there that shoots these uranium-235 atoms or nuclei and releases a bunch of energy. And as that energy is released, it goes into this water tank, and it heats the water into steam. And then that steam goes to a turbine, and it actually turns this turbine. So this is a turbine. And that turbine, when it turns, actually creates a bunch of electrical energy that's can be used to power a small town. You know, you see these things all the time with nuclear power plants, these big towers. Those are called cooling towers, and the cooling towers is just where this hot water goes. You know, when this turbine's turned, it actually creates some hot water, and it goes to that cooling tower to cool, in case you're wondering what those towers are. And the second most common use of fission reactions is actually to make a bomb. In fact, that's the original use of fission, was to make a bomb to drop on the Japanese during World War II, I think. Yes. Okay, so that being said, the way that a fission bomb basically works is you've got your little core sample of uranium-235 and a particle accelerator that shoots it, causing, you know, this nuclear fission reaction. Massive amounts of energy is released. When it hits the ground, it blows up and makes this giant mushroom cloud that kills a bunch of people. So here's what a fission equation might look like. I have two of them for you, actually. So the fission of uranium-235. Uranium-235, when you wing a neutron at it, so plus a neutron, is going to produce either barium and krypton, so barium-140 and krypton-93, and 3 neutrons that would then fly off into other uranium-235s and split them. Or you might get, instead of barium and krypton, you might get xenon-144 and strontium-90. It really just depends on how that uranium splits. And then 2 neutrons that would fly off and hit other uranium-235s and split them. So you are not going to be responsible for completing a fission equation, but you have to be able to recognize a fission equation when you see one. And some easy ways to recognize a fission equation is that you're going to start with a somewhat large nucleus. So you'll notice uranium-235 is big, right? And you're always going to be adding a neutron to it. So there's always going to be a plus neutron on the left-hand side. Anytime you see that, that's certainly going to be a fission reaction. And of course, there are a number of things that you need to know about fission. The first thing you need to know about fission is that it doesn't occur naturally anywhere. Nowhere in the universe that we know of does fission occur naturally. It was a man-made process. In fact, we paid a bunch of scientists back in the 1940s to go to the Nevada desert and figure out how to fission an atom to release its energy so that we could make bombs for war. Just so you know, that was called the Manhattan Project. Fission reactions release massive amounts of energy, more energy than you'll ever get from a chemical reaction. Another thing is that the byproducts of fission are often radioactive elements, and they would need to decay over time. And those radioactive elements, those byproducts, that's your nuclear waste. And they need to be stored somewhere where they can safely decay and not get into our environment. So back up here where we talked about the decay products, these products right here are often radioactive. And so we need to store them properly so that they don't get into our water and hurt us. The other thing is that when we were trying to figure out how to fission out an atom, not every atom is fissionable. In fact, there are only two fissionable isotopes, uranium-235 and plutonium-239. And those are the only isotopes that we've ever been able to put through a fission process. And of those, uranium-235 is the most common. And so that's the one you're going to see the most being fissioned. Fission reactions are relatively easy to achieve, meaning that all you got to do is have a particle accelerator and a sample of a fissionable isotope, and you can make this happen. You just have to wing the neutrons fast enough that when they collide with that unstable nucleus, they will split it into pieces. And the other thing that you need to know is that atomic bombs are fission bombs, meaning that whenever you hear someone talking about an atomic bomb works off of a fission reaction. And that fission reaction, by the way, I didn't mention it up here, and so I should add it. When I said that it releases a massive amount of energy, that's about 1 million times greater than any chemical reaction. So think of any kind of fire that you can think of that's not nuclear, or any bomb you can think of that's not a nuclear bomb, and you multiply that by 1 million, that would be the amount of energy released by a fission reaction. All right, let's spend a moment talking about what fusion is. Fusion is sort of the opposite of fission. Fusion is where you take two smaller nuclei. So for example, you can have something like this is called hydrogen-2, which is deuterium, or hydrogen-2, and tritium is hydrogen-3. And you can join the two together into helium, a whole bunch of energy, right? Because you're that strong nuclear force, you're actually creating that strong nuclear force. And that releases a bunch of energy. And of course, in this particular case, you also get an extra neutron that just kind of shoots out and goes off on its own. So this is fusion. All right, so the uses of fusion. Well, the only use that we have for fusion, which we have been able to achieve fusion here on Earth, is for a nuclear bomb. In fact, the name of the bomb, so nuclear weapons, and the name of the weapon that can be made is called a hydrogen bomb. And the way that a hydrogen bomb works is that you've got your, your fusion chemicals in here, and usually that's hydrogen-2 or hydrogen-3, so deuterium and tritium. And then you actually have this fissionable material. And so maybe uranium-235 or some plutonium-239 in the core. And so what happens is that to start a fusion reaction, you need a massive amount of energy. So this fission bomb or reaction starts first, and that provides the energy to fuse these two things into our helium, right? And then that releases, of course, even more energy. So here's what a fusion equation might look like. So the first one is helium fusing with hydrogen to form lithium. And then we've got the second one, two heliums fusing to form beryllium. Or, of course, the one that we started with. You've got, say, hydrogen, deuterium, and tritium, so two isotopes of hydrogen joining to become helium and a neutron. So those are three examples of fusion reactions. Now, it's easy to tell fusion reactions because you're always joining, so you've got two small atoms and you're joining them together, so that would be considered a fusion reaction. So let's talk about a couple things you need to know about fusion. First thing is that fusion is actually a natural process, but just not here on Earth. So fusion actually takes place in stars like our sun, which explains a lot about why the sun is so hot, because it's a giant nuclear explosion, right? It's creating a bunch of helium from hydrogen fusing to each other, and then of course that's creating a huge amount of energy that is used to basically power our entire planet. Fusion reactions require a very large input of energy, meaning that in order to even start a fusion reaction, you need to actually force your two nuclei together. I mean, you've got, two nuclei that have positive charges, and you're trying to force them close enough together for that strong nuclear force to take over. And this requires a huge amount of energy, which is why this doesn't happen naturally here. It happens naturally on the sun because it already has all that huge amount, that big amount of energy, very, very hot, 1,000,000 degrees Celsius temperature that would force those two nuclei close enough together for a fusion reaction to take place. And for this reaction, fusion reactions are very difficult to achieve in a controlled environment. So we have not ever been able to actually fuse two hydrogens together in a lab. We've been able to do it in a bomb, and that bomb, explodes and kills a bunch of people, but we've never been able to control it in an environment where we could actually stand near it and not get hurt. Fusion bombs are called hydrogen bombs, and we just went over, up here, what happens in a hydrogen bomb. So atomic bombs are fission bombs, hydrogen bombs are fusion bombs. And remember that a fusion bomb, a hydrogen bomb actually requires a fission reaction to start it. And that all goes back to this, because a fusion reaction requires so much energy, that energy in a bomb comes from a fission reaction first, starting the fusion process. Fusion reactions are the reactions that started or happened during the Big Bang to create all the elements. So all the elements on your periodic table were created through fusion reactions. And the last thing that we need to talk about fusion is that fusion releases 3 times more energy than fission. So that's everything we need to know about fission and fusion.